Hello Math 1224, this is Dr. P with Lesson Launch 18.2, the pyramid. So in this video I want to talk about how we can calculate the sum of this infinite series here, which we'll just call it S. Now again, you'll notice that this series has some features similar to those of a geometric series. You'll notice there's a 1/3 to the 0, 1/3 to the 1, 1/3 squared, 1/3 to the third, and so on. But this is not a geometric series because the ratio of one term to the next is not a constant. That is, the ratio that I multiply this by to get this term, I believe that would be 2 times 1/3. And then to multiply this term, in order to get this term, I would need to multiply by, I don't know what I need. I think I need 3/2 to cancel those factors. And then I need 3/2 times 1/3. So I'd be multiplying by, I think, 1/2. And then to get this term to this term, I'd need to multiply by 4/3 times 1/3. And it turns out that's not one constant ratio between terms. So this is not a geometric series. Not geometric. Even though it looks kind of like it. Alright, so we're going to need some other technique to figure out what this sum is. So I'm going to show actually two different techniques. One of which uses the ideas that we've discovered in this chapter, and then the other of which is just kind of clever and cute. I'll start with clever and cute because I always favor clever and cute. So the way that I'm going to think about this series is I'm just going to start by sort of thinking about it verbally. I've got one of these, and two of these, and three of these, and four of these. So it's kind of like I have a stack. I'm going to draw a visual over here. Like I've got a stack of terms. I've got one of that first one, and then two of that second one, and then three of that third one, that second power of 1/3, and then four copies of the third power of 1/3, and so on. This keeps going, of course, infinitely. All right, so that's one way of looking at this series. Is I have, and that's why I'm calling this a pyramid. By the way, it's kind of like an infinite pyramid of terms. And what you're seeing here is the result of trying to calculate the sum in this direction. That is, calculate one of these, and then two of these, and then three of these, and then four of these, and then five of these. But what if I tried calculating the sum this way instead? So in other words, suppose I take one of each of these, one copy of this, one copy of this, one copy of this, one copy of this, and so on. So that would give me 1/3 to the 0, plus 1/3 to the 1, plus 1/3 squared, plus 1/3 cubed, and so on. Well, that would be a geometric series, and I could find its sum, which I will do in just a little bit. But then what would I have left? Well, then what I'd have to have left would be one more of these, two more of these, three more of these, and so on. So I could actually separate these out. I could write down another sum that looks just like that, and that would be another geometric series, just starts at a different place. Okay, so now altogether I've got one of these, which is what I want. I've got two of these, which is what I want. I have two of these and I need three of these. I've got two of these and I need four of these, and so on. So I'm going to write down another sum, which begins with 1/3 squared, and then 1/3 cubed, and so on. That's another geometric series. And then I'm going to write down another geometric series, which begins with 1/3 cubed, and so on. Now, by the way, each of these is a geometric series. I know it looks like this one has only one term, but you got to remember, there's other terms over here. These terms go on forever. And there's going to be another one below this that starts out with 1/3 to the fourth. So I could call these, I don't know what I want to call these. I hate calling them S1, S2, S3, because they're not partial sums of this series. They're something else. So instead, I think I'll call this T0, and then T1. Let's see, where do I put this? T1, and then T2, and then T3, and so on. Now, let me back up a little bit so that I can have room to write down the sums of these. So the sums of these geometric series, I can calculate using the geometric series formula. So this T0, for example, its first term is 1, because 1/3 to the 0 is 1, and its common ratio is 1/3. See, that actually is a geometric series, because now I can bounce from this term to the next, from each term to the next, by multiplying by 1/3. So that's a geometric series, and its sum is 1/1 minus 1/3. By the way, just in case you need a reminder, geometric series sum for an infinite series, provided it converges, you always got to check that, and I'm not really doing a very good job of doing that here. But you'll notice in each case R is 1/3, which is less than 1. Actually, my absolute value of r is what's important there. So that guarantees each of these will converge. Anyway, this sum is, that's 1 over 2/3, that's equal to 3/2. And then this next one here, that's the first term, 1/3 over 1 minus 1/3. So that's 1/3 over 2/3, that's 1/2, I believe. And then this one here is going to be 1/3 squared over 1 minus 1/3. That's going to be 1/6, I think. And this sum here is going to be 1/3 cubed over 1 minus 1/3. That's going to be 1/18. By the way, you may wonder how I'm getting these so quickly. I'm getting them quickly because I'm noticing that in order to get from this one to this one, I'm just multiplying by 1/3, and then this one is 1/3 of that, and this one is 1/3 of that, and so on. That's where all these numbers are coming from. And then you'll realize that this, what I have here, put this in a different color now, all this is another geometric series. That one also goes on forever. So the sum of that geometric series in total is going to be the first term, 3/2, over 1 minus the common ratio, which is still 1/3. Still 1/3. And that's going to come out to, I believe that is 3/2 over 2/3, which comes out to, a little more room there, comes out to 9/4. Now, I don't know about you, but I have to say, if you looked at this, if you were able to just glance at this series here, and you were able to say, oh, that's going to be 9/4, then you should get a medal, or maybe a steak or something, because that is not at all obvious from looking at that, is it? But that should be equal to 9/4 just by straight up algebra, really. Everything here you might have learned how to do in your algebra class in high school. Didn't really need much calculus to think about. But now I'm going to show another approach which does require calculus. It's a little bit more conceptually heavy, but if you can master this, then you can master a whole class of problems which may or may not look like this. And also, it's just kind of cute. So again, I'm going to try this strategy of backing out. Now, what does that mean again? That means, first of all, I'm going to write this sum using summation notation. And then I'm going to try to stick a variable in there. That is, think of this as a Taylor series. Think of the sum as a Taylor series. That's going to be a little bit trickier this time than in the last video. I picked a little bit harder example on purpose. Okay, but this first part I think should not be quite so bad. The first part should be just this S here. S is the sum from k equals 0. Let's see, I think from 0 to infinity of 1/3 to the k multiplied by, what am I multiplying by? I don't think it's k exactly. If it were k, that first term would be 0 times 1/3 to 0. I think it's actually k plus 1. K plus 1. So that's my sum as an infinite summation in sum notation. Okay? So that's step 1. Step 1 is done. Check-a-rooney. Check. Okay, now for step 2. So now I want to think of this S, this sum, from k equals 0 to infinity of k plus 1 times 1/3 to the k. I want to think of this as a Taylor series of some stripe. Or as a power series. Actually, more generically, in this section, section 10.3, we're not going to care whether the series that we're working with are Taylor series, like whether they were actually gotten using Taylor's method or not. We're just going to care that they are power series. So thinking of this as a power series, I could think of this as the sum from k equals 0 to infinity of k plus 1, x to the k, where x is equal to 1/3. Okay, so that's what it is I'm trying to figure out. So basically I'm trying to figure out what in the heck function is this anyway? What function is this? Okay, well, it's a series. It's a power series, and it's the sum from k equals 0 to infinity of k plus 1 times x to the k. That is a totally reasonable answer to what function is this. It's just not extremely helpful. It's not helpful if I want to get this into some kind of closed form that doesn't require a sigma notation. So we're going to try and simplify this a bit. Now I want you to look at this for a second. Look at k plus 1 times x to the k, and think about, is there anything special about that structurally that is just remarkable? Anything about that that looks special? You know, one thing that I notice about this is that this is, well, k plus 1 times x to the k, that is the derivative with respect to x. It's the derivative of x to the k plus 1, which means I could think of this, series this is the derivative of this infinite sum, k equals 0 to infinity of x to the k plus 1. Now that's interesting. What does it mean for that to be the derivative of that series? Well, I believe I could actually say something intelligent about this series here, because what kind of series is this? It is a power series. It is a Taylor series, but it's a very special kind of power series. This is a, what is this? This is a geometric series. And its sum is the first term, which is x to the 1, because when you look at the k equals 0 term, this gives you x to the 1. So its sum is x to the 1, or just x, over 1 minus the common ratio. And the common ratio that takes one term to the next is x. So this thing here, this is really, this is d dx of x over 1 minus x. And I can actually calculate that. Now, by the way, all of this is equal to this series here. This is what I'm calculating here. This right here. I've never stepped away from this. So this sum is what I'm about to calculate here. So this derivative is, oh brother, now I have to, have we done the quotient rule once in this course? No, I guess we owe it to ourselves to do it once. Okay, what's the quotient rule? Let's see. How does that thing go? It goes ho-de high, minus hi-de-ho over ho-ho. I don't think they let you say that version in school anymore. That, like, most people do low-de high minus high-de-low over low-low, because it became forbidden at some point to use the word ho in school. Anyway, this comes out to, what is that? That's 1 minus x, and then plus x. I believe that's just 1 over 1 minus x squared. And I believe that is exactly what this is. The sum from k equals 0 to infinity, 0 to infinity, of k plus 1, x to the k. So that is the sum of that series. And when x is equal to 1/3, this gives me the sum from k equals 0 to infinity of k plus 1, x to the k, 1/3 to the k. That is equal to 1 over 1 minus x, that's 1/3, squared. Well, that's 1 over 2/3 squared, which is exactly 9 over 4. Same thing we got earlier. Let's zoom out, see if we can find it there. I think I made the mistake of making my work a little bit too much like a tower, more tower than pyramid, I think. Anyway, so there's two different ways of getting the same thing there. You notice I got 9/4 up here and 9/4 down here. And it probably seems like we did a heck of a lot of work to get this solution here. This was solution 2. And this was solution 1. Okay, now first of all, let's not be unfair here. Solution 1, it wasn't that much shorter than solution 2. It's just I had zoomed out at some point, making it seem smaller than it actually was. But solution 1, we had to be kind of clever, and we had to have this pyramid idea here of separating those terms out. And it's actually kind of a handy idea. You can use it on more than one series. I wouldn't have bothered with it otherwise. But this solution number 2, this generalizes to a pretty large class of problems. I hope I've started to convince you of this now. So anyway, those are a couple of examples of using Taylor series to think about just straight up numerical sums, numerical infinite series. And in class, we're going to see some more techniques for developing Taylor series and applying them to solve problems. So that's it. 25 minutes today. Huzzah! I'll see you in class.